C prime. Maybe let me say smooth. Irreducible curve in X, right? Just because just because when we defined algebraic equivalence, we considered there exists a curve and a line bundle here that restricted to L tilde and over one point of C and restricted to O over the other point of C. And here we just can take just this thing and the line bundle restricted, right? So and now what does it mean that line bundle is algebraically equivalent to some other line bundle on a curve? What does it mean algebraic? What is algebraic equivalence on a curve? What is about the corresponding divisor? This means, okay, we will consider this in a complex setting, and then I will explain it in a complex setting more accurately. This means that the degree of the corresponding divisors are equivalent, right? And last time, when we consider an intersection form, we saw that this thing is an intersection of L, right? And now we know that this is trivial. So line bundle L tilde is trivial, okay? And in a complex setting, we will discuss why this is so, why algebraic equivalence means an equivalence of degrees, because in some sense, oops, oh no, I will explain this in a complex setting later. Okay, and now what I should say next? Okay, yes. And there was two equivalence relation, and the numerical was the chorus equivalence relation, and of course we immediately see that numerical group of X is a free abelian group, endowed with an intersection form, with a non-degenerate intersection form. Induced by the intersection form that we considered last time. Is it clear that this is a free group? So we have a symmetric pairing on numerical group of X.
Sorry, why is it free?
Because we have no torsion here, just because if line bundle is equivalent, is equivalent to a trivial line bundle, then N is equal to 0 for all line bundles in the Picard group.
Okay.
And this means that this We have a free abelian group with an intersection form, with a non-degenerate intersection form. Yes, and now let me state a proposition that we will prove in the complex setting, but it works in a more general setting of algebraic varieties, but for arbitrary field, as far as I understand, okay, I will say later. So, neuron series group of X and its quotient X are finitely generated abelian groups and the rank of neuron series group, or in fact numerical X, is called the Picard number of X. This is denoted by rho X, and this is by definition rank of this finitely generated group. So we will discuss why this works in complex setting, but in fact it works for any fields. But a proof is not difficult, but as far as I understand, we need to discuss Hilbert schemes and so on to give a short proof of this fact. And maybe we will discuss this later, but not now. Okay. Yes, and now let me state the Hodge index theorem, because now we will discuss what are these groups, neuron severity, numerical X, and Picard group of a K3 surface, of an algebraic K3 surface. And to explain something about intersection form on them, we will need the Hodge index theorem. The Hodge index theorem. So we can state it in the following way: the signature of the intersection form on numerical X, not that we consider here intersection form, induced intersection form on numerical group of X, not Picard group. It's important. Is 1 rho X minus 1. So maybe let me also formulate it more precisely, the statement, because here we don't understand why we need our surface to be projective here. So let me give a more precise statement of the Hodge index theorem. This tells us that for an ample line bundle L on X and a line bundle that is not numerically trivial, that isn't numerically trivial, that is orthogonal to L, to an ample line bundle, we have L its intersection with itself is strictly less than 0. Okay, so when we have an ample line bundle, when we have a numerically non-trivial line bundle that is orthogonal to L, then its self-intersection is strictly less than 0. Okay, this is the statement. And now let me formulate proposition for K3 surfaces. Yes, for algebraic K3 surfaces, all these groups, numerical group, Néron-Severi group, and the Picard group are just isomorphic. Proposition. For an algebraic, this is important. For an algebraic K3 surface S, the natural surjections are isomorphisms. Natural surjections. So we always have surjections from Picard S to the Néron group of S, Néron-Severi group of S, and to the numerical group of S. And in the case of K3 surfaces, here we have isomorphisms. Okay? And moreover, the intersection form, the intersection of pairing, intersection pairing on Picard group of S is even non-degenerate and of signature -1. Okay, so last time someone asked me about whether the Picard group of S has torsion or no, and this proposition immediately says that no, it has no torsion, and we will see why it doesn't have torsion even when we consider complex K3 surfaces. I mean non-algebraic ones. But let me first formulate it for an algebraic K3 surface.
Excuse me, what is even form?
This means that it's 0 modulo 2 for all line bundles. Okay?
So all squares are
Oh, yes,
Okay.
all squares are. Okay, and now let me give a proof of this statement. Proof. So suppose L is non-trivial. line bundle, non-trivial, but L L prime is 0 for all for just for an ample line bundle, for an ample line bundle L prime. What can we deduce from this about our line bundle? So L, suppose that we have a global section on S that is not equal to 0. In this case, S corresponds to an effective divisor C on our surface S.
Do we always have such section?
No. Suppose. Now we. So what I want to show that we don't have such a section, just from Riemann-Roch theorem. So suppose, or even no, even not just Riemann-Roch, just from the property of intersection form that we discussed last time. So suppose that we have such a section. Then it corresponds to an effective divisor on S, and then what we have? We have an intersection L0 that is in this case equal to an intersection. And what is this? We discussed this last time. What is this?
Degree of L prime on T.
And what we know about this?
C could be singular or not reducible.
But suppose that we have a line bundle, then we can consider the corresponding effective divisor. But in any case, it's an effective divisor, and L prime is an ample line bundle. What we know about the degree in this case?
Larger than 0.
Yes, this is strictly greater than 0. Everyone understand why?
I also have the same question with Alex. That maybe C is, for example, is non-singular. It has singular points, or it has different components. Because it by no means is the same.
But let us take one component, okay?
Okay.
And so then we can just add, and we will, in any case, we will obtain greater. What we need here that if it has several components, okay, we will take just the sum of this, and this will be greater than 0. Okay? Just everyone understand why we take an ample line bundle, then this is greater than 0. Right? Yes. So, and you see here we have this equation. We suppose that it's 0. So from this we obtain that there are no global sections of this line bundle L. And in the same fashion we what is it in English? Similar. For the dual line bundle, we also don't have global sections of L dual. Just the same thing. We suppose that it has global sections. Then we will obtain that this degree will be strictly less than 0, and we suppose this when we consider L. So, and now by set duality. H2 has L is 0. Just because this is H0 is L2. I always forget about it. Okay, this is 0. And now by Riemann-Roch, Riemann-Roch theorem tells that polar characteristic of a line bundle L is equal to what?
2 plus 1/2 of the self-intersection.
And now what we know about this Euler characteristic from all these computations? We know that
This one positive, it's minus here 1.
so it's strictly less than 0, right? Just because we know that H2 is 0 and that H1 is
We
0.
have also H1 equal to 0.
Yes, because by set duality. So look, here we proved that this is 0, here we proved that this is 0, and from set duality we obtain that H2 is also 0. So this is...
You said that H1 is 0.
It may be 0, we don't know yet.
Yeah, but what we need is that it's just less or equal to 0, what we need. And from this, we immediately obtain that is strictly less than 0. It cannot be 0, because otherwise we will have here 2, right? And this means that L is numerically non-trivial. Numerically non-trivial. We see that the Picard group, that the numerical equivalence on an algebraic K3 surface, there are no numerically non-trivial line bundles, so we have this isomorphism, right? And in particular for neuron-Savory group.
But we considered only ample line bundles L prime.
Yes, it was enough. So we suppose here that there exists a line bundle, right? But we first take a non-trivial line bundle, and we want to show that it's numerically non-trivial, right?
Okay.
If it will be numerically trivial, then we definitely will have this vanishing, right? And from this, if it's not equal to 0, then L is already numerically non-trivial, right? If it's non-zero with some ample line bundle, and if it's 0, we show that its self-intersection is non-zero.
Mm-hmm.
So from this we obtain this identification. That here I should write this. Sorry. Here I should write K3 surface, and in the complex setting we will see that this is definitely doesn't work for all varieties. This is a very rare property because we have non-trivial so-called Picard variety. We will discuss this. Okay, and now, so we get anisomorphisms, and from this we see that the claim about signature immediately follows just from the Hodge index theorem, because we have this anisomorphism, and why self-intersection is even just by Riemann-Roch. By Riemann-Roch the self-intersection is equal to 2L minus 4, and this is equal to 0 mod 2. Okay?
Yeah, but I have an extra question about the definition. That previously we defined Picard rank using the rank for numerical equivalence.
No, we define it, but it's the same because numerical equivalence and neuron severity, numerical group and neuron severity group are distinguished by torsion. So we can have torsion in neuron severity group, and we never have a torsion in numerical group of X. But it doesn't matter for the rank of the corresponding.
How to prove this result, or
About what? About rank?
about their rank are the same? That only torsion elements are killed by.
I can say maybe after I will think and I will answer why they're changed transparent. But in any case, usually we can define Picard rank just from neuron severity group. Okay, this is a standard definition. Okay, and now what we let me also state lemma. That for all K3 surfaces, in fact, I will briefly mention this also later. For non-projective K3 surfaces, we don't have these isomorphisms. We will for all K3 surfaces, we will have just this thing. We will discuss this in the complex setting, and non-projective ones and non-projective K3 surfaces can appear only in the complex setting. So always we have this identification, but this is not true because we don't have Hodge index theorem in the general case, because Hodge index theorem is about ample line bundles. But in any case, for all K3 surfaces, even non-projective, there are no torsion. There is no torsion in Picard group of S. Proof from Riemann-Roch theorem for L torsion line bundle, its Euler characteristic is equal to 2, which means that L or its dual by shear duality is effective. So there is a section, global section of L or its dual. But suppose that there is a global section for L on S. Then there is it induced a non-zero section of its power right for all. Okay.
But why L or L dual is effective?
Just from this, because it's positive, and also we use third duality as usually. So this means that H0 or H2 is non-zero, because what is this? This is H0 minus H2 plus.
Okay, yes.
H, and here we need to use third duality. Now suppose we have a section of L, then we have a section for all non-zero sections for all powers of L. Yes, and moreover, zero locus, zero sets of S and its power coincide. So if we know that, and from this we immediately obtain that L should be trivial, because if it is torsion bundle, there exists K such that L is trivial, and there is a non-zero section of trivial line bundle, so it should be identical. So the corresponding zero sets is just zero, and here we have just zeros. And this means that L is, from this we obtain that L is trivial. Okay? Do you understand? Mm-hmm. Great. And now let me come to the complex setting where we have. So first of all, in the complex setting, an especially nice feature is that we have a singular cohomology. So we can consider H as Z. And now let me just, and also we will meet Hodge decomposition, and let me just state it for now without proof. Decomposition, because today we will just use it as a statement, and it's yesterday I didn't understand how to explain this very, very briefly. So the Hodge decomposition, okay, tell us what? Tell us that K cohomologies of Z with the complex coefficient can be decomposed in the direct sum of the following homologies of sheaves on S H E S. So usually the thing is denoted by just H P Q of S P Q Q pi. So usually, so what is this theorem about? So we have a this holds for any Keller variety. Any Keller variety. Here I need to write A plus Q is equal to K. Here I need is equal to K. So for any Keller variety, we can consider just sheaves of holomorphic forms on it and compute its cohomologies. And the statement is that just singular cohomologies of S, tensor C, can be decomposed in the following direct sum of the complex subspaces in such a way that H Q S is just conjugate to H Q P. Okay? This is a statement. And today we will just use it many times in what follows too. So, and also in the complex setting, so this is it, I just formulate this statement, and now in the complex setting we also have the exponential sequence. Exponential sequence that will explain us what is the relation of Picard group with the neuron Severi group in a more precise way. So what is an exponential exact sequence? We can take just that, mapping by 2 pi I to, okay, maybe here I need, okay. The exponential exact, for now, let me come back to the general setting of any, maybe not just surface, but for smooth line surface X. No, variety. Let me formulate it in general. First, in a because all these are general statements. So we have an exponential exact sequence. Here we have invertible sheaves, and this is just an exponent map that maps a function to the exponent of 2 pi I f. Right? We have such an exact sequence in the complex setting. And for smooth variety, this will give you a long exact sequence of cohomologies. Of course, here we have 0 just because for connected varieties, this part, 0 cohomologies will give you exact sequence. So here we can write 0, and here we have x, z, mapping to x, x, mapping to x or x invertible. H2 xz. And now, what is this group?
Car.
So here I have Picard variety of x, always. Right? Everyone understands this? And now, what is this map?
Chern class.
This is the first Chern class. And what Hodge theory tells us that this embedding gives you a lattice inside. So from the Hodge theory, we obtain the following exact sequence. I will explain in a minute. This annotation is mapping to Picard group. And this, in fact, your first Chern class gives you a map to a neuron Severi group. Okay, what is this? This is so-called Picard variety. Picard variety of X. And what this? This is just, we take H1 xz. So this is a torus, and in fact this is, in complex settings, this torus is always algebraic. So our Picard group is an extension of two groups of a very different nature. So first is this this algebraic torus, Picard variety, and this is a discrete part. This is a finitely generated group. Finitely generated group. So maybe all that I need to explain here why the image of the first Chern class gives you neuron-Severi group. Maybe do you understand this, or I need to explain? Объяснить? Okay. So, but
Explain, please.
yeah, okay, I will explain. We just need to. I just need to remind what is this map topologically, and I will remind you in a minute. But before, let me state that if we will prove now that. So what you need to prove is that the image of the map C1 is isomorphic to neuron-Severi group of X for any variety. But before this, note that from this we immediately obtain finitely that neuron-Severi group is finitely generated, just because this is an image of C1, so this is a quotient of H2XZ, and this is finitely generated group. Okay? So in the complex setting, we just for free obtain this statement about finitely generated. And now let me explain this thing. So what is C1 topologically? So suppose we have a smooth curve. Okay, and maybe here, let me explain for X a surface. What is topologically? So suppose that C is an irreducible curve. Then we can consider the restriction. H2 CZ. And this will give you a linear form on H2XZ. So by congruality, using congruality, we obtain an element inside and from this description, why do we obtain a neuron-Severi group? What we need to show is that if we have two line bundles that are algebraically equivalent, then their first Chern classes will be equivalent. And so, why it's so? Because how do we define algebraic equivalence? So we have a curve, right? We have a surface X here, and we have two embedding of X using 2 points of C. Right, and there was a line bundle L that was restricted to.
You write the first Chern class of L1 and the second Chern class of.
Oh, sorry. Mm-hmm. Then the first Chern classes coincide. So what we have here is that the pullback of L is isomorphic to L1. And the pullback of L is isomorphic to L2. This is just an...
Maybe it should be X on the right.
X. Sorry. And we have these two things, and note that these two embeddings are homotopically equivalent. Okay, and from this, PQ homotopically equivalent, and from this topological description, we obtain that C1, their first Chern class is coincides. Okay? Just because, so, was this clear or no? No?
Why is it homotopically equivalent?
Just because the first embedding is an embedding of xp, and the second one xq. And this was connected curves. This is important. For a connected algebraic curve, if we have 2 points on it, then we have homotopically equivalent embeddings of x, right?
Yes.
So, and from this topological description, we will obtain equivalence of the first Chern classes. Okay? So, what next? Yes, and also in the complex setting, maybe a remark is that the bilinear form on the Picard group of X comes from the bilinear form on neuron Severi group of X that induced by the topological cup product, by the cup product in the second cohomologies. Okay, so in the complex setting, this intersection form comes from topology. Okay, and now what we obtain for a K3 surface. So from the exponential exact sequence, we obtain what immediately? For
Since the first Chern class is an embedding car into H2.
Yes, we have an embedding of the Picard group inside H2. Okay. And moreover, and also, we always have an isomorphism of Picard group with the neuron Severi group of S. And I already mentioned that for a numerical group, for non-algebraic K3 surfaces, there is no, maybe we will discuss an example later. This is not true for a non-algebraic. This can happen for a non-algebraic. Yes. Okay. And now let us compute. Okay. Let us compute. Hodge diamond of S. Hodge diamond. What is Hodge diamond? for a surface, this is the following numbers. H1, H2, H11, H20, H21, H12. So for a scalar surface, this сейчас, блин. This thing is always symmetric. In this, in a horizontal line, and in a vertical line. And what is the Hodge diamond for a K3 surface? For any K3 surface, in all characteristics, and for non-projective ones too, but we will compute it just in a complex setting because I want to use Hodge decomposition. So for a K3 surfaces, the Hodge diamond looks in the following way. Okay, so this is the statement. This vanishing we obtain just from definition, and also because so what is Hodge decomposition of this is S omega S O plus H1 S OS, right? And now we have just by definition the vanishing of this thing, and we know that these two complex spaces are conjugated to each other, so we obtain this thing. So we immediately obtain this. H00 is obviously equal to 1. This is just the Poincare duality, and what we need to compute is the thing. So, so first of all, what we have is decomposed in the direct sum of H2 S of S, H1 S plus H0 S omega 2 S. Okay, and what this is just one-dimensional complex space, just because we know that this is trivial. So using Hodge theory, we obtain immediately that this is C, and
this is just circularity.
what or whatever you want, or singularity, right? This is or from duality. So it remains to compute this thing. And to compute this thing, it's enough to compute what is the dimension of the second cohomologous. And here we can use Noether formula. That tell us what? That tell us that the earlier characteristic of structure sheaf for any smooth surface. This is the self-intersection of canonical class of S. So this is just so. And last time we have computed this. What is this for a K3 surface? 92.
24.
24. And now from this we obtain that H1O1 of S is equal to 20. Right? Just because this is the usual Euler characteristic and this is an alternating sum of its cohomologies. Oh, S minus 1 E from 0 to 4. Right?
So for any surface, you can compute the Hodge number in the middle if you know the other numbers and the self-intersection number of the canonical device.
Yes, please, and let me give you an exercise, because I didn't give you an exercise before. Please compute Hodge diamond of a complex torus. Diamond of a complex torus. Okay, and we know that all complex torus, not just abelian varieties, all complex torus are Keller, so we can use Hodge decomposition, and also we have Noether formula, and so we can compute it exactly in the same manner.
Does it also work in higher dimensions? Or does it also work in higher dimensions to find the Hodge number in the middle? Or
What work?
this method, does it also work in higher dimensions?
Yes, yes. This is an exercise, so you can exercise. I explain you all formulas because all formulas that I state work in for a general surface. So
I mean, in higher dimensions.
in higher dimensions we have our Hodge diamond is bigger, so sometimes it's not so easy to compute it, but here it's easy. Okay, so we have 10 minutes. Maybe it's time for unramified and ramified covers. Okay, and by the way, I found an answer to your question, and this is a Hirzebruch-Riemann-Roch formula. And I'm not sure that I want to explain what is dot class and Chern character for now, but if you know what's this, you can immediately obtain how does Euler characteristics of structure sheaf for unramified covers related to each other. Okay, this is a consequence of Hirzebruch-Riemann-Roch. So, and now, what coverings? Hope that this time will be last time. I'm trying to explain some. So last time we discussed that the cover is a finite subjective morphism of normal schemes and we discussed the formula times OXR, where R was a ramification divisor. That parameterized singular points of the corresponding morphism. And so now let me define branching orders. branching orders of pi, and I will define it algebraically, okay? For schemes. So suppose that our ramification divisor, suppose that, so our ramification divisor is a direct sum of irreducible components. G is an irreducible component of R. And now what is the branching order? So suppose that we have xj and rj a general point. In a scheme theoretical sense, okay? I want to define this thing algebraically. So, and we have the corresponding xj local ring, one-dimensional local ring. It's one-dimensional just because its dimension is a codimension of the corresponding variety, and the corresponding variety is just a divisor. So, and our morphism pi gives us a morphism of local rings p xj the corresponding local isomorphism, and then we will define J branching order in xj as the following. So we can consider the ideal that is generated by the maximal ideal of Pxg. And we know that this local ring is one-dimensional, so this ideal is just some power of the maximal ideal of Xg. And this power is exactly branching order. Okay? So this is exactly as we considered in for curves, when we as you considered for curves for Gurwitz formula, but here we just need to consider general points of the corresponding irreducible components of the corresponding divisor. Okay? So, and geometrically this corresponds, I will already explain this, this corresponds branching order, measure how many points in fibers are glued in it. Okay, so general fiber is, for example, n points. Sometimes we can have n-1 points, and branching order is how many points are glued together.
Can I say here that EJ is just equal to RJ on the left-hand side?
What?
EJ is just equal to RJ on the left-hand side.
Yes. And now I will state that RJ here is just IJ minus 1. So let me state the statement. Let me state. Maybe I need. So lemma. Maybe I will just formulate it without proof, because this is just a local computation, that in fact R is a direct sum of RG, and the corresponding coefficients are just AG minus 1. And this is a local computation just because we define R using the forms of maximal degree, and if you will compute everything locally using this thing, you will obtain that the corresponding coefficients are ig-1. Okay? And now let me formulate what is going on for cyclic covers. I can explain this if you want, but this is just because we used formula for canonical classes for cyclic covers. So let me remind that what was the setting. So we had a smooth connected complex manifold. We have an effective divisor. Effective divisor on it, and the corresponding line bundle was a tensor power of some line bundle on it for a line bundle L. So now let me define what is the corresponding cyclic cover geometrically. This is the following thing. So consider the section S on Y. The section that vanishes along B. Now,
So this is just by definition, or you define cyclic if the...
no, I will define cyclic using this data. So an effective divisor and a line bundle such that its tensor power is equal to the corresponding line bundle. So n roots from the corresponding line bundle. And in fact, here B can be trivial. Can be trivial. We will discuss this. So, and we have a section, just because this is an effective divisor and this is the corresponding line bundle, S. And now let me consider, maybe let me denote it in such a way, L, B, X, where L is the total space of L. So this is the corresponding affine bundle, right? And now what we have? We have a tautological section on L of the pullback of L. There is a tautological section just by definition of the pullback, right?
So X and Y are the same, right?
No, we didn't define X. We will define it in a minute. For now, we want to define a cyclic cover from this data. And now I will define
We
X.
don't have X.
Huh?
It should be
It's
Y.
morphism.
Wait, oh, sorry. Here is a B. Yes, sorry. Yes, this is an affine bundle over Y, and now we have a tautological section, and now we will define X inside L as the zero divisor of the pullback of section S minus Tn, okay, on L. And I claim that the restriction of P to X will give you a cyclic covering of Y, okay? And now let me state without proof, sorry, the statement. So, okay, I will just formulate this. No, maybe I will not formulate it, or, okay. Be the answer cover of branched along B. And you see from this definition that, of course, the branching locus is exactly B, right? Branching along B. And let B1 be a reduced divisor y minus 1 from B.
What is reduced?
Reduced is this mean that reduced scheme. So the pre-image of B, of course, is not reduced. It's I will state now that it's n times B, and we consider just the corresponding underlying scheme. Okay. Then OX B1 is isomorphic to the pullback of L, where L was along B. L was isomorphic to B. The second thing is OX is that the pullback is in fact n times B1. So n is the branching order. And this is more or less obvious because over B we have n points glued together. And the third formula that we used when we discuss Kummer surfaces is that Kx is just the pullback of Ky O times n minus 1. Okay? And I write down these two things just because this is a consequence of what we proved before. Is Y O times R, right? And now we know that this is a direct sum of Rj with a branching order minus 1, right? And from this we know that n is branching, this is the corresponding ramification divisor is n minus 1 b1, and this. So from this we obtain this formula. Okay.
Why do we have n minus 1 but not n?
Because if this is a branching order, we have proved that the ramification divisor is a direct sum of branching orders minus 1 times
Yeah.
Rg, like in a Horwitz formula. And
Okay.
here n is branching order. So here we should have n minus 1.
Mm-hmm.
Okay?
Yes.
And in fact, I can leave it as an exercise. It's not so difficult from this geometric description.